Hey, pre-calc students, this is Mr. Beck. Today we're going to talk about our very last section that we're going to be learning this semester. It involves working with logarithmic properties and solving equations that are exponential or logarithmic and using those properties. So what you should see here, first of all, is properties where it lists properties 11 through 20. These are really the exact same properties that we had on the previous day's notes, but the reason why it goes to 11 through 20 is because the Microsoft Word is thinking it's still part of a list. So it just renumbered them for us. Very first problem that I have to work with is a problem that looks like this. Now this is 3, and then the 2, an exponent. The exponent is really this whole logarithmic expression. So if we have a situation like that, first thing that I notice is both of these logarithms have the same base. So if we can combine them into the exact same exponent, or the exact same logarithm, we're in pretty good shape. That's what I did up here. Now, what I wanted to show with this problem was actually one of our exponential properties. If you remember, if we have the exponential expression, I'd say not use 3 because I'm already using 3. Let's say a to the m times a to the n, that equals a to the m plus n. So if you remember that property from exponents, this is actually working with that property backwards, where what we have here is we have that addition of the exponents. What we're going to do with that addition is we're going to turn the addition of the exponents into multiplication of the bases. So if we do that, we'll see this expression we have right here, which if you notice is really what this is, but it works with it on a logarithmic level as opposed to working with it, or working on an exponential level as opposed to working with it on a logarithmic level first. So for part B, if I have 2 to the log base 4 of 25, lots of different approaches to this problem. I love this problem for that reason, that one of the approaches that we could take is we could turn 25 into 5 squared, bring the 2 out in front using one of our log properties, and then this throws students for a loop also, that 2 times log base 4 of 5 as the exponent. If you remember, let's go ahead and say a to the m to the nth power equals a to the m times m, and those are both in the exponent. Let me erase that. So a to the m times n. Now we're really working with that property backwards. And one of the things you'll see about this section is we have to use our exponential properties backwards so that we could work with logarithms in them as well. So in doing that, working with it backwards, I'm going to take the 2 squared to the log base 4 of 5, which gives me just log base 4 of 5, or 5 is my overall solution. Secondary approach that I've had students take is, well, if this is a base 4, why don't we turn 2 into a base 4, which is 4 to the 1/2 power. If we do that approach, then what ends up happening is we can then bring the 1/2 to the exponent, and that's how we'll get 5 in that situation. What this kind of leads us to see is if we have these exponents that are the same, what we could do is we could really write the first expression as a second expression. This is the unofficial property I have, property 21 there. But this goes to the nature of what logarithms do for us. Logarithms allow us to work with let me point them out. So our anti-log here, working with the anti-log and the base, this is really showing a representation of the ratio of these two numbers to each other. And it's those two numbers on an exponential level. And if they're the same exponent, then all you have to do is worry about the numbers as opposed to what the exponents are. So just another example of how logarithms work and what they are. For problem number C. Problem number C, log base 2 of 25 times log base 25 of 64. One of the things I had my students do in class was I had them say, okay, this is what I got on the calculator, this is what I got on the calculator. And to do that, I get an answer of 6, which means something special has got to be going on here. Well, to determine what the special thing that's going on there is, it's good for us to be able to take a look at it and say, what is the change of base? Now, the change of base is really properties 19 and 20 here. Properties 19 and 20, they're probably some of the most important properties because that's how a lot of students can type some of those logarithms into their calculator. So let's start off with property 20, that log base a of m. So log base a of m is the common log of m over the common log of a. So basically, we're going to take the common log of the anti-log or the common log of a. Now, it doesn't have to be the anti-log or the common log. It could be the natural log. In fact, I prefer using the natural log mainly because As you work further and further in mathematics, you only work with the natural log. You very rarely work with the common log unless you're working with the financial system. But working with, or scientific, meaning like the metric system. But the natural log of m over the natural log of a. What I'm going to be doing for this problem is I'm going to do just that. So I'm going to turn log base 2 of 25 into the natural log of 25 over the natural log of 2. Do the same thing for log base 25 of 64, natural log of 64 over natural log of 25. So again, that's a change of base, and it's an important property that we need to make sure that we know and know very well. In doing so, what you should see is these natural log of 25s reduced to 1. And then this again throws students off, and it's using that that property backwards. Natural log of 64 over the natural log of 2 is log base 2 of 64, which in turn that can reduce, or that can simplify to 6. Now, we didn't have to use the natural log here. As I said, we could have used any base. Just for fun, I said, we could use base 60, log base 60 of 25 or log base 60 of 2. And I had students do that in class, and what happens is the ratio of those numbers ends up being the exact same thing of 6. So again, show how logarithms work. Problem number 2, this is really just an extension of some of the problems that we did in day 1, just to kind of rehash that, okay, if I have this logarithmic expression, one of the things that I can do is I can break it up into different logarithms. More importantly, let me kind of get rid of these. More importantly, one of the things that I do look at is how many factors are inside the natural log. If I know how many factors are inside the natural log, it tells me how many terms this is going to be broken into. So 6x squared, the cube root of that, 5, and x plus 7 to the 4th power gives me 5 individual factors. And hopefully you guys remember that factors are separated by multiplication and division. So what I'm going to do is turn that into 5 separate logarithms. So 1 natural log and 5 factors turns into 5 separate logarithms. So each logarithm that had the factor in the numerator is a positive natural log. Each one that had a factor in the denominator is a negative natural log. So, and if you notice, I ended up taking these expressions out, or these exponents out in front to begin with, or like in this process. So, but if you notice what I've highlighted is, if I rewrote this so that I have negative exponents, what ends up happening is you see why the logarithms are actually negative as opposed to positive. Problem number 3 here. So what I ended up doing here was I first combined all of my 3 terms into the natural log of 3 factors. And when I did that, then I take e to both sides. By doing e to both sides, I will get y equals cx squared over x plus 1. Property number 4, one of the things that we're going to do is just work with it that log base 33 is 1, log base 39 is 2, log base 327 is 3, et cetera, all the way up to x. Now, the idea behind this was showing that this turns into what we call x factorial, so factorial. What x factorial means, in this case, 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. There are a lot of properties, probability, which is where you're going to find it in your calculator, the PRB button. So there are lots of probabilities where we're going to end up multiplying those. And in terms of like, I don't know if you ever heard of like combinations of permutations. We have formulas that we can work with, but as we're choosing, it's going to be like you have 5 options and 4 options and 3 options, so you end up multiplying those options. So, moving right along, what I have here is this equation. So the first equation I want to work with here is what happens if I have just a simple expression like so. Divide by 3, just kind of like what we did last time. Now I can turn that 125 into 5 to the 3rd, and then take log base 5 of both sides. And that's what we see here, log base 5 of both sides. Then solve for x, we get x equals 1. The question is, what happens if we don't have the exact same base? So if we don't have the exact same base, what different types of things are going to occur? Well, the way that we do this ends up being kind of formulaic, which is why I wrote down an approach. you don't have to follow everything in this order, but this is typically what I do. And I've been doing these problems for many, many years, and I just follow the exact same pattern. So I start by taking the natural log of both sides, then bring that exponent out in front of each side, then distribute and distribute. So when we distribute, we get x natural log of 2 minus natural log of 2 equals natural log of 5 plus 2x natural log of 5. Then third step, or I guess fourth step now, bring all the x's to one side. So that means this x and this x have to be brought to the same side through subtraction. Bring everything else to the other side. And we do that so that we can factor out the x. We're left with that factor, which then we divide both sides by that factor. So really, start by taking the natural log of both sides, bring the exponents in front, distribute. That way we have individual terms, and we rearrange the terms so the x's are all on one side, factor out that x and divide. So when we do that, we get an expression that looks like this, and that's great to type into a calculator, but we could use logarithmic properties to combine those into one expression, and then change the base formula to take it into what our overall answer is. And I like to have this in terms of one logarithm. So problem number 7 is sort of the same thing. I ended up skipping it just because it was a little bit more crazy. So problem number 8. Now this is one that I'm definitely going to make sure you want to know how to do. So to do that, we're going to again use the property I showed before, where multiplication of the exponents, I could rewrite it as the base to one of those exponents to another exponent. And in doing so, you end up with a quadratic. And so if you remember last time we had a logarithmic quadratic, this is now an exponential quadratic. The exponential quadratic, if we do a u substitution, gets it into this quadratic form. So this is really it's a function within a function, so a composition of functions. We've worked with them before. Factor like usual, and when we do that, we get u equals -2 and u equals 1. Now, in doing so, one of the things that we have to remember is we're not really solving for u, we're solving for x. And in order to solve for x, we have to resubstitute and then take log base 3 of both sides. Now, if you notice, log base 3 of a negative is no bueno, so x is log base 3 of 1, which we can simplify as 0. Problem number 9 is really the same kind of thing, but the way that problem starts is it looks incredibly different. Now, one of the things I do want to point out is, do you notice how we have 3 individual terms to start off with? These problems are different from the other problems because we really have a combination of multiplication and division. In this case, we have base to an exponent equals base to an exponent, but this is 3 individual terms, which kind of prompts us to say, I think this looks quadratic. So first step is turn the 4 into a 2 squared. And if you remember the property we did before, multiplication of the exponents, we could rewrite that as 2x squared. Second one, property that I used before, special property, addition of the exponents, we can write as multiplication of the same base. So then that 2 squared is 4. After that, bring everything to one side, which is what I did in that step, and use substitution, u equals 2 to the x. So we can see it in its quadratic form. Factor that u equal -6, u equal to 2. Resubstitute, and in resubstituting and solving, we have logarithm of a negative, which is again no bueno. Then 2 to the x equals 2, so we have log base 2 of 1. For problem number 10, this one's definitely a tougher one because this requires us to actually use the change base formula and use it accurately. We have log base 2 of 3x plus 2 and log base 4 of x. Because we have different bases, we have to use the change of base formula. I turned this log base 4 of x into log base 2 of x over log base 2 of 4. Why 2 is the big question? Because this is a 2 and I want to use the same base. So then log base 2 of 4 I know is 2. So I multiplied both sides of the equation by 2, and in doing so, I ended up having a 2 here, which I then brought as the exponent, so it's no longer out in front. 2 times 1/2 is log base 2 of x, and 2 times 3 is 6. So then I combine into one logarithm, take 2 to both sides, so 2 to both sides, and I have this expression. From that expression, then I'm going to do 2 steps in one. I'm going to multiply that out to give me that expression, multiply both sides by x, so it's 32x. Then bring it over, and I have a quadratic again, which that quadratic factored gives me x equals 2 ninths and x equals 2. Last but not least, I have problem number 11. Now there's a typo in this problem that was supposed to be e to the x minus e to the negative x. So first step is I multiply both sides by 2. Then I'm going to multiply by e to the x, which sounds kind of strange, but the reason why is e to the x times e to the negative x is 1. And so I end up with only positive exponents. E to the x squared minus 1 is 6e to the x. Bring it over, and now we see the quadratic form again. So u equals e to the x. So u squared minus 6u minus 1. This one does not factor, so quadratic formula. And be careful this mistake. I have 6 plus 2 square root of 10 when I simplify it over 2. A lot of students only want to take one of those numbers over 2, but you have to take both of those numbers over 2. And then set e to the x equal both of them. Now 3 minus the square root of 10 is negative, and when we solve for x, we get the square root of a negative, or the natural log of a negative, which is bad. And so the only answer is the natural log of 3 plus the square root of 10. Hopefully you followed. Kind of short and sweet, but using properties. And one of the big ideas behind the properties we're using today is composition of functions, which is why composition of functions is in this chapter. In fact, that's how our chapter 5 began. So what happens when we have a function within a function? Here we see exponential functions within quadratics. We also before saw logarithms within quadratics. So anyway, it's been a great semester, everybody. Stay tuned for next semester.